Welcome back to CST432. Today we are looking at sensing the environment. In this topic, we will look at the typical microcontroller peripheral logic blocks that are used in most microcontrollers, as well as some of the specific hardware architecture for the LEGO MINDSTORM. As we try to understand more about I/O peripherals, the question that we should keep in mind is how are I/O peripherals interface to the microprocessor or microcontroller? First, we will look at what are some of the microcontroller blocks found in a typical microcontroller. First, there is the microprocessor core, which is the same as in any other microprocessor, which is the brains of the CPU. Then, typically we also have permanent memory storage, such as ROM, EEPROM, or E2PROM, that can be erased electrically. Third, we will have volatile memory storage, such as SRAM and dynamic RAM. And then we have the interrupt logic, which controls the reception of signals generated by peripherals to trigger events in the microcontroller. And finally, we have the I/O device logic, which is used to support different peripherals and different types of applications depending on the microcontroller. We shall now look at some examples of I/O peripheral blocks. One example would be the LCD or external display controller, such as that used for controlling a VGA or DVI or HDMI output. Secondly, we may have a keyboard scanner that takes input from a resistive matrix keyboard. Then, in most modern systems today, we may encounter a resistive or capacitive touchpad controller that is either stylus driven or finger driven, that allows us to accept multi-touch inputs to control the device. And also we will have general purpose I/O or GPIO, which is used to control miscellaneous logic circuits using the independently defined signals. Then we may find serial device interface buses. This allows multiple peripherals to share one data line to be connected to the microcontroller. Examples of these include the Serial Peripheral Interface Bus or SPI Bus, as well as the Inter-IC Bus or I2C bus. Finally, we have timers. Timers are used to trigger events in the microcontroller. Timers and pulse width modulators are often found in a microcontroller peripheral I/O block. This allows us to perform pulse measurements using input signals to determine the duration or the sequence of events, and then also to generate pulses, which is using output compare devices to trigger a waveform to be sent out through the I/O interface. Next, we have various other types of devices, such as the digital to analog or analog to digital converter. These are variously known as ADC or DAC. Then we will have other interface buses, such as the Universal Serial Bus or USB, as well as other peripherals like real-time clocks, co-processors, including FPUs or floating point units, digital signal processors or DSPs, and so on, and dedicated hardware and software codecs, which are more and more found in devices today used for audio and video encoding and decoding. Finally, some advanced microcontrollers may even include programmable glue logic, such as a programmable gate array and other reprogrammable logic that can be used to program or define specific functions needed by the microcontroller. This is the block diagram found in the Atmel AT91 SAM7S microcontroller used in the NXT. For example, we may find at the top the ARM7 processor core. Then there is also the debugging interface using the JTAG hardware debugger, as well as the system controller, the memory controller, the RAM, the SRAM stored inside the die of the controller, the flash memory, as well as other circuitry related to the memory interface. Next, we see the various timers used for controlling and generating clocks in the microcontroller, as well as the various serial communications interfaces. On the left, we see the Universal Serial Synchronous Asynchronous Receiver Transceiver or USART interfaces, which are used for implementing RS-232 and as well as RS-485 interfaces. On the right, we see the various output compare and timers and other controls for controlling generation of signal and other pulses. Finally, we have the SPI, which is the serial peripheral interface, as well as the analog digital converters. In addition, we also have the timers used for triggering various events in the microcontroller. We shall now go over the various blocks in quick succession. First of all, it's a debug and test, or DBGU block. These are used for hardware and JTAG debugging interface. Then there's the reset controller used for triggering a CPU reset in hardware. The real-time timer, which is a freeze-running seconds counter that can be used for implementing a real-time clock for the microcontroller. We also have the periodic interval timer. Now, this is an important block because it generates periodic interrupts for the operating system process scheduler, and this controls the system timer counter, or SysTick, in NXOS. Finally, we have a watchdog timer, which is used to reset the processor in case any system process or the application process trigger a deadlock, then is unable to recover from it. Then we have the voltage regulator mode controller, which allows us to switch a microcontroller to standby mode, so save power when it is not being used. There's also the memory controller for controlling access to the RAM to remap the RAM addresses from a different address to starting from address 0, which is the start of memory. We also have the embedded flash controller, or EFC, used for controlling access to the flash memory for writing new information. The flash programming interface, or FFPI, is used for hardware programming of the microcontroller during production. And finally, we have the peripheral DMA controller, which is used for DMA transfers between the built-in devices and the RAM that does not involve the CPU to copy the values from one register in the peripheral device to the memory location in memory. Next, we have the Advanced Interrupt Controller, or AIC. This is an important block for the microcontroller because it manages the interrupt sources and their priorities in order to control which interrupts are triggering in the microcontroller at any given time. Then we have the clock generator, which is a hardware block for master clock signal generation, and this gives all the various clock signals used by the blocks as well, including all the serial communications blocks. Power management controller will provide processor clock, the master clock, as well as the USB clock signals for use by the USB subsystem. In terms of I/O interfaces, the parallel input-output controller, or PIO controller, generates various digital signals independently of each other for controlling all the miscellaneous devices and output signals used by the system. Now, in this case, for the next, it is used for sensor port digital I/O lines and so on. The serial peripheral interface is an important 4-wire external peripheral bus protocol used for controlling dedicated peripherals in the next brick. For example, it is used for LCD display control. Finally, we have the 2-wire interface, which is a different serial bus interface which controls external peripherals using only 2 wires using the I2C protocol. And in this case, it is used for interfacing to the AVR coprocessor, which is the one in the next used to control the various motors and drive the power to the motors. In terms of the various serial communications blocks, as I mentioned previously, there is the USART, which is a bidirectional asynchronous serial communications interface. In the case of the next, it's used for interfacing to the Bluetooth module, which is used for Bluetooth communications. In addition, a different USART is used for configuring or controlling the RS485 high-speed serial interface that can be used to connect between multiple next devices. The synchronous serial controller allows for bidirectional synchronous serial communications, however it is not used in the next. Finally, the timer counter has 3 different 16-bit interrupt-driven timers that can be used for various events and timing triggering of action routines. And it is used for various device driver timing interrupts in the next. A pulse width modulator controller is another block in the Atmel microcontroller. It provides 4 PWM channels for generating square waves with varying frequency and duty cycles. In the case of the next, it's used for speaker control in the firmware to allow us to generate various tones and even simulate audio files output in the next speaker. The USB device port allows us to connect a full speed or 12 megabit per second interface to a personal computer for downloading and other communications between the NEXT and the PC. Finally, the analog to digital converter allows us to perform 10-bit precision A to D conversions over 8 different channels. We shall now see how all these various microcontroller peripheral blocks are interfaced in the NEXT hardware. The NEXT hardware architecture diagram shows us the connections. First, we discuss the coprocessor interface. In the next break, we have the main processor, which is the Atmel ARM7 processor, and there is a coprocessor, which is an Atmel AVR low-end device used for controlling the motors as well as other miscellaneous inputs. So the AVR coprocessor actually has interfaces to the physical buttons on the front of the NEXT brick. In addition, it uses the I2C bus to transfer the information between the AVR and the ARM processors. As mentioned, the AVR coprocessor provides control for the motor actuator outputs. It also performs the A to D conversion for the analog sensor inputs, as well as to give power to the motors and the sensors, and to determine the front panel button status and report it to the ARM processor. The ARM AVR I2C bus operates at 380 kilobits per second, which is the high-speed version of the I2C interface. The interface connection between the AVR coprocessor and the ARM processor implements certain constraints. The first is that the I2C messages are exchanged between these two devices every 2 milliseconds. This means that the shortest possible interval for motor output control is 2 milliseconds between any updates. Secondly, the A to D conversion requires 3 milliseconds to provide a new reading, and this means the sampling interval should be 3 milliseconds or greater between one sample to the next sample. The reason for this is due to the legacy RISC sensor requirements. Next, we look at the hardware control interface for the motors. In this case, we have the motor power control coming from the AVR coprocessor to generate the required power output in terms of the current and the duration of the drive to the motors. The motors have servos that would provide a tachometer readings that is returned directly to the ARM processor in order to determine the position of the motor at any given time. There are 3 output ports available for motor control: port A, port B, and port C. The motor power control provides a sustained 700 milliamps output current, but at the peak you can supply up to 1 amp of current. However, it is limited by the various fuses programmed into the AVR microcontroller output chain. The output is a pulse width modulated signal, and it can be either configured to break, meaning that it will stop the motors turning when the output is disabled, or float when there is a break in the signal. So if the break signal changes, the motor will continue moving if it is already moving. So 2 input pins are used as tachometers to measure the servo motor angle of revolution, and this is read directly by the ARM microcontroller. Next, we look at the sensor ports. There is the analog sensor input coming from the AVR coprocessor, as well as the digital signal interface, which is a 9.6 kilobits per second I2C interface defined by using a so-called bit bank technique on the ARM processor to the external sensor. The sensor ports are numbered 1, 2, 3, and 4. Now, port 4 has an alternative function as a high-speed serial RS485 interface. The analog input pin is connected to a 10-bit A to D converter on the AVR coprocessor. So it is not read directly by the ARM controller, but instead we have to receive the information through the AVR message transferred between the AVR controller and the ARM processor. In addition, 2 digital I/O pins are available. These are used for GPIO controls for analog sensors, such as for the light sensor, it turns on the LED light to illuminate the scene that we are trying to determine its light intensity for. Secondly, for digital sensors such as the ultrasonic sensor, it acts as a 9.6 kilobit per second I2C communications channel with these sensors. Now, this 9.6 kilobits per second is implemented using a software-driven output control on the various GPIO pins. As mentioned, the I2C protocol is software-based for interfacing to the sensors. The interrupt driver generates clock and data pulses, and the NXOS ARM debug uses the open drain logic configuration on the I2C data line, where the ARM first pulls the data line high, and then the data transmission from the sensor to the ARM controller is performed by pulling the data line high and low to generate the values of 1 and 0 on the data bus. However, the next firmware configures the I2C data line as push-pull logic. What this means is that if the sensor needs to transmit data to the controller, the ARM will first switch the data line from output to input, and then data transmission from the sensor to the ARM controller will occur. There's something to take note of when we are using sensor port 4. First of all, the RS485 high-speed serial interface is multiplexed to the port 4 digital I/O lines. In normal operation, the port 4 should be able to support all analog and digital sensors. However, when we are using NXOS ARM debug, it may not work reliably with all digital I2C sensors on port 4. Reason for this is because it does not use the same scheme as the next standard firmware in performing data transfer between the sensor and the next controller. So in our case, we found that it does not currently function properly with the LEGO ultrasound sensor, but it may function with other third-party sensors. So for safety, it is best to avoid using port 4 for digital sensors using the I2C protocol when using NXOS ARM debug. Next, we look at the display interface. This uses the SPI Bus for communications with it. In addition, the SPI Bus is also connected to the Bluetooth or Blue Core module. The LCD panel has 100 pixels horizontally and 64 pixels vertically. This display is connected via the SPI Bus as mentioned previously. In addition, the LCD is completely refreshed every 17 milliseconds, meaning that the entire image presented to the LCD panel is updated once every 17 milliseconds. Now, in order to program the LCD, the bitmap maps 1 byte to 8 vertical pixels. This means that if you want to display text, we must first encode the ASCII character as an index into a character bitmap lookup table, where the entries in the table contains column by column image of the bitmap for a character. So in NXOS, we use 8 bits vertical by 5 bit horizontal pixel formats, meaning that each character is stored in 5 bytes, and these 5 bytes are copied to the screen whenever we want to display a particular character. Next, we look at the Bluetooth interface. The Bluetooth interface actually has 2 communication channels with the ARM microcontroller. The first is the SPI Bus, which is used for firmware programming of the Bluetooth module. However, this is reserved and is not normally used by software. The second, or more commonly used interface, is the UART bus, which is connected using 460.8 kilobits per second. In terms of operation, the Bluetooth device can control 3 other next as slave devices, which supports the Bluetooth serial port profile or SPP profile. The Bluetooth module is a separate microcontroller connected via the SPI Bus, which is only used for firmware upgrade or reprogramming. Therefore, it is reserved. The more commonly used interface is the Bluetooth data interface, which uses the UART, and it operates at 460.8 kilobits per second as mentioned previously. Next, we look at the USB interface on the next break. The USB interface signal is connected directly to the microcontroller. It provides a 2.0 version full-speed controller interface, which provides 12 megabits per second data rate. In addition, it supports 4 endpoints, where EP0 or endpoint 0 is the control endpoint, which allows for bidirectional control command communication. Secondly, we have the EP1 and the EP2 bulk data pipes, which are unidirectional pipes used for transmitting data from the PC to the next, as well as from the next to the PC. So each of these channels use up one of the endpoints. Finally, the EP3 endpoint is unused. Finally, we have the sound driver, which is controlling the speaker on the next. The sound driver is PWM driven, meaning that the output from the PWM module will be used to drive the sound circuitry. The speaker is controlled directly by the ARM microcontroller. Pulse width modulation output signal is used to control the frequency of the tone. However, in NXOS ARM debug, we use a different interface which is using the timer counter to control the speaker output signal, and that triggers the output in software controlled or defined manner. For further information, you can refer to some of the references listed here. That's all. See you next time.